Hello, my name is Edmund Saliklis and I teach in the Architectural Engineering Department at California Polytechnic. This is my department's logo. We are in the gentle rolling hills of the central coast of California. What am I talking about today? I'm talking about equilibrium without statics. I've developed a method that can find external reactions that equilibrate a structure as well as internal forces and moments. I don't use graphic statics. I don't use algebraic statics. And the answer is perfectly correct for gravity loads because it is based on the Müller-Breslau method, the so-called influence line method that Heinrich Müller-Breslau created. But I have recreated it and I'm calling it the modern Müller-Breslau method because I can now handle lateral loads as well. And there are other interesting side paths that we are exploring, for instance, buckling. The most important idea right now is that I hope a revolution has begun. A revolution that was similar to the revolution sparked by form and forces by Allen and Zalewski. And that revolution was greatly aided by my co-conspirators in the IASS who took it way further. I want that to happen with this method. This method is fun, it's visual, it's geometric, it can be used for our own engineering students, certainly for architecture students, construction management students. I even created a general education course for non-technical students. And I think we can use it to reach out to children in the kindergarten through secondary schools. The method uses only one equation. It's an energy equation. The unknown is the thing I'm looking for. I perturb it, I make it move a little bit, and then I watch how the forces applied to the structure are lofted up in space, how they travel through space because of that perturbation delta. Now, here's a beam with a pin support at the left end, a roller here, and then overhang. Heinrich Müller-Breslau could have found this left reaction by perturbing a unit amount all the way up to here, but then the beam stretches. In the modern method, the perturbation happens, but the beam follows a circular path. All boundary conditions are maintained. Here is the loft that is created by the perturbation delta. Here's another loft. Some are positive, some are negative. We could do this for internal moments as well. This theta is the perturbation. The unknown is the moment. The loft is at the centroids of the load on either side of the kink. Very easy to calculate with a quick sketch even, and the answer is exactly correct for small perturbations. For trusses, we could do this as well. And for trusses, it's really fun because suppose we're looking for this bar force on the top chord. I stretch it. I simply stretch it. And then I watch how the forces are lofted in space. And I simply measure it. That's it. And as the perturbation gets smaller and smaller, the answer approaches the exact theoretical answer. Now, this is exciting, and I want to thank my colleague, Professor Graham Archer, for helping me on this. A horizontal grid of beams here. Suppose I wanted the column force at one of the edges of the grid. All of the members are simply supported. They do not transfer bending moment. I could do this on a napkin sketch. Ladies and gentlemen, we could just sketch this out. Why? Because everything has to go along similar triangles. We march along the edges of the perturbed shape, never ever ever in the hyperbolic space here, always along the edges, and then we just draw similar triangles. And the answer is exact. And that is the so-called table napkin sketch or serviette sketch that is so wonderful and so enticing for our students. Suppose we wanted to find the tributary area flowing into the beam on A1 to B2. Ladies and gentlemen, we use this for live load reduction. What is the tributary area on this beam? In the modern Müller-Breslau method, very quick. I could do it on a napkin. I lift up that beam, I perturb it a unit amount, and I march along the edges of the perturbed shape. And there is my napkin sketch. immediately establishing, using that one equation, what the unknown is, and for a unit force per area, boom, I get the tributary area instantly. Not the force on the beam, but the tributary area. We are beginning to do really interesting things with indeterminate structures. Ladies and gentlemen, this is a little different. Here you have to know how it looks due to a specific perturbation along one edge of the structure. You never, ever need to find out the deformed shape due to the loads. You only find the deformed shape due to the perturbation, and then you just apply the loads and you measure these distances. Here is the black magic now. Watch this. A buckling problem, super complicated, drawn up by Wai-Fa Chen and Eric Liu, and they used second order differential equations, and I used this children's program GeoGebra. And as the perturbation gets smaller and smaller, we approach the theoretical exact answer. Now when people see that, they say, what sorcery is this? Hopefully you are curious enough to know how to get the answer. The answer is go get the book, Equilibrium Without Statics. It will be published at the end of 2021. Once again, the perturbations are due to the unknown, never due to the load, and the loads are applied at the centroids, which makes this thing easy to do on a napkin sketch. So please come visit me in California. We'll go mountain biking. This is Morro Bay, a 150-meter rock, and we can go ride our mountain bikes and talk about equilibrium. Thank you.